Okay, now we're going to look at some more challenging circuits. These ones, what happens if we have two batteries in different locations. So if you had two batteries like so, just had two batteries like this. Like if you had like a 6 volt and a 3 volt, that just is the equivalent of 9 volts. But the question is, what happens is when you have two batteries in different locations in the circuit. So we touched upon this last day. We know that the current into a junction or node. So remember, if we have a point, the current into a junction must equal the current out. And the other one was recognizing that if you look at any loop, the voltage provided by the battery must sum to 0 when we lose the voltage across the resistors. So here's our first example we're going to look at. So basically what it comes down to is we're going to be creating a system of equations and then using algebra to solve them. So let's scroll down. So this is the circuit we will look at first. So we have 3 volts here, and this one's pointing upwards, and we have another battery right over here. So again, it's complicated because they're parallel to each other, and we have a couple resistors around. So whenever you approach these, oftentimes we don't know what direction the current is. So I've just kind of defined as the current is, so you kind of just take a guess. So I'm going to say current in this path is going clockwise, and it's going to go down against this 1.5 volt battery, and it's going to go down against the I3. So what's going to happen is if all your values for current comes out positive, it means yes, we guessed the correct direction. We did everything, everything's good to go. However, if one of your values come out to be negative, the magnitude, if assuming you did everything correctly, the magnitude is correct. Negative means that you guessed the wrong direction. I think we have an example like that coming up when we have a negative value. Or might be one of the examples later on. But for now, let's just solve this problem, and we're going to use nodal analysis. So basically what's going to happen is we're going to look at all the current going into different nodes. I'm going to first redraw that circuit just on the top right, just so we have something to refer to. Okay, let's just first redraw that circuit. So again, we have a battery, which is 3 volts, and it passes by a 150 ohm resistor, a node, a 100 ohm resistor, and a battery, and another 150, and a 200. So 150, 200, 1.5. So I defined the current as traveling this way. So this is I1 going in this direction. I said I2 is going down, and I3 is going around this clockwise direction. Again, you just take a guess, doesn't really matter. Before you continue, you might want to draw some plus or minus. So if the current is passing through in here, we're going to be gaining like so. We're going to lose some potential across this one. We're going to lose potential. Batteries always have the positive on the big end. We're going to lose potential like so. So because current is going clockwise, you have to lose potential as we go through that battery. Okay. Okay, so let's start this. Let's get a black pen. So for node analysis, we're going to look at what's happening in our two nodes. Here's node 1, and here's node 2. So first of all, if we're looking at node 1, we say, okay, at node 1, current's going in, so I'm going to say I1, and based on my definition, I said I1 is equal to I2 plus I3. Now we need to create 3 other equations. So we're basically going to look at each path. So here's one path. We're going to see what's happening with I1. So what's happening with I1? So we know that current is voltage divided by resistance. So node 1 must have some voltage. We don't really know what that voltage is. I'm just going to define it as V1. So node 1 has some voltage V1. But we know the current that's going to be traveling through, the I1 value. If I want to solve for that, I1 is just divided by the voltage lost across that 150 ohms divided by 150 ohms. So I1 is equal to 3 volts minus V1. Right, so here's 3. We know we have 3 volts of potential right there, V1. Node 2, we actually know that V is equal to 0 there because notice the negative end of both batteries is pointing towards node 2. So therefore we know it must have 0. Like this bottom area has to have 0 potential. So I'm going to divide this by 150 ohms. All right, so let's not put let's just leave with numbers. For I2, again, we're going from looking at this middle path now. So to find out how much current is traveling through the 100 ohm resistor, we know we're starting at V1. And then we're going to lose voltage from the 1.5. It's like pushing against divided by 100. You can also put a minus V2 there, but we know V2 is equal to 0 for this problem. Sometimes it might not be equal to 0. We might not. Some different value. And then lastly, we have I3 is equal to V1 minus V2. Okay, V1 to V2, that's we know it has to drop down to 0, divided by 150 plus 200. So now we have a series of 4 equations, and we can combine them. So notice how we have I1 is equal to I2 and I3. So originally we know that, but now we can create a single equation that consists of just V1 as our unknown. So I1 is 3 minus V1 over 150. And that's equal to I2, which is V1 minus 1.5 over 100. And plus I3, which is V1 over 350. And now it's just a matter of math. So easiest way, lowest common denominator, is equal to 2100. Now there's different ways you can do it. So we end up with 42 minus 14 V1 is equal to 21 V1 minus 31.5 plus 6 V1. Combine them all together, do some math. We have V1 is equal to 1.793 volts. So now we saw it must be that many volts there. And now if we go put this back into our other 3 equations, we can solve for our individual currents. Therefore, we get I1 is equal to 0.0080 amps. I2 is equal to 0.0029 amps. And lastly, I3 is equal to 0.0051 amps.